On May 29, 1919, Arthur Eddington pointed his telescope at the sun and changed everything. The entire Newtonian universe hung in the balance. The strangest part, he was technically breaking the law of physics he was trying to prove. For 2 minutes and 9 seconds, the moon slid perfectly across the face of our star, and the light from distant Hyades stars had to make a choice. They would either travel straight, as Isaac Newton had insisted for over 2 centuries, or they would bend around the sun's mass, confirming a radical new vision of reality proposed by a German patent clerk. That clerk, Albert Einstein, had spent the previous 8 years wrestling with a problem that had haunted physicists since 1859. That year, Urbain Le Verrier, the French astronomer who had discovered Neptune with nothing but mathematics, noticed something deeply wrong. Mercury's orbit was drifting. Its closest point to the Sun, the perihelion, was shifting by 43 arcseconds per century, more than Newton's equations could explain. It was a tiny discrepancy, 1/10 the width of a human hair held at arm's length, but it was real, and it would not go away. Einstein had already shattered physics once. In 1905, his special theory of relativity had revealed that space and time were not separate absolutes, but a single, stretchable fabric. But that theory had no room for gravity. So in 1907, sitting in his chair at the Swiss Patent Office in Bern, Einstein had what he later called the happiest thought of my life. He imagined a man falling from the roof of a house. While falling, the man would feel weightless. He would not feel his own gravity. And from that simple image, Einstein realized something profound. Gravity and acceleration are locally indistinguishable. He called it the equivalence principle. For the next 8 years, Einstein chased this idea through a labyrinth of tensor calculus and non-Euclidean geometry. He had to learn mathematics that barely existed, invented by Bernhard Riemann decades earlier. By November 1915, he was exhausted, arguing with the mathematician David Hilbert in Göttingen, who was racing him to the same equations. On November 25, 1915, Einstein presented his final field equations to the Prussian Academy of Sciences in Berlin. The room was small. The audience was confused, but the equation on the blackboard was a new law for the universe. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. Gravity was not a force pulling across empty space, it was geometry. The sun did not pull on Earth, it warped the fabric of spacetime around it, and Earth was simply following the straightest possible path, a geodesic through that curved landscape. Imagine a bowling ball placed on a stretched rubber sheet. The sheet dips. Now roll a marble near the edge. The marble does not fall into the ball because of a mysterious attraction. It follows the curve of the sheet. That is gravity, and it was beautiful. But Einstein needed a prediction. The precession of Mercury's orbit fit perfectly. His equations accounted for the missing 43 arcseconds without any fudge factors. But the real test was something Newton could not explain at all: light bending. Light has no mass, so Newton's theory predicted no deflection. Einstein's geometry predicted a deflection of 1.75 arcseconds for starlight grazing the sun. But you cannot see stars next to the sun unless the moon blocks the blinding light. You need a total solar eclipse, and in 1919 one was coming. The war had ended only 7 months earlier. Europe was exhausted, its observatories damaged, its astronomers scattered. Eddington, a Quaker and a pacifist, had spent the war years in Britain, while Einstein's work was branded as enemy science. Many British scientists refused to even read German papers. But Eddington was different. He was one of the few people on Earth who truly understood general relativity. And he knew that a solar eclipse on May 29, 1919, would pass directly in front of the Hyades star cluster, the densest group of bright stars visible near the sun. It was a once-in-a-lifetime alignment. If he missed it, the next opportunity would come in 1922. The Royal Society and the Royal Astronomical Society jointly funded 2 expeditions. Eddington himself would go to Principe Island, a Portuguese cocoa plantation colony off the west coast of Africa. A second team, led by Andrew Crommelin from the Royal Greenwich Observatory, would travel to Sobral in northern Brazil. 2 locations, 2 telescopes, 1 shot at catching the same stars bending around the same hidden sun. Eddington arrived on Principe in April. The weather was brutal, humid, overcast, tropical storms rolling in almost daily. He set up his astrographic telescope in a clearing near the plantation house, fighting rust and insects. As the eclipse date approached, the sky refused to clear. On the morning of May 29th, it was raining. Eddington later wrote that he practically gave up hope. But at 10:30 p.m., just minutes before totality, the clouds parted. The moon slid into position. For 302 seconds, just over 5 minutes, the sky went dark, and the stars of the Hyades cluster became visible next to the eclipsed sun. Eddington took 16 photographic plates. The first showed nothing. Cloud had ruined the exposure. The second was usable, but faint. He developed them on the island, in a makeshift darkroom, using a thermometer borrowed from the plantation's chicken incubator. When he looked at the glass plate under a measuring microscope, he saw it immediately. The stars had shifted. Not by much, less than 0.002 of a millimeter on the plate, but the shift was real, and it matched Einstein's prediction, not Newton's. Meanwhile, in Sobral, Crommelin's team had perfect weather. They took 26 plates using 2 different telescopes. One telescope produced sharp, clear images. The other, due to a lens defect, gave fuzzy results that were later discarded. When the Sobral plates were measured, they confirmed the same deflection, approximately 1.98 arcseconds, slightly above Einstein's 1.75, but far closer to his prediction than to Newton's 0. On November 6, 1919, a joint meeting of the Royal Society and the Royal Astronomical Society was held in London. The room at Burlington House was packed. Astronomer Royal Frank Dyson stood and announced the results. After careful study of the plates, I am prepared to say that they confirm Einstein's prediction. The audience erupted. The Times of London ran the headline the next day, "Revolution in Science, Newton's Ideas Overthrown." Einstein became a global celebrity overnight, but there is a deeper story here, one that the newspapers missed. Eddington had selectively chosen which plates to emphasize. The Sobral results, when averaged with the Principe data, gave a deflection of 1.61 arcseconds, lower than Einstein's prediction. Eddington discarded the lower values from one Sobral telescope, arguing the lens was flawed. Modern historians have debated whether this was scientific judgment or motivated reasoning. Eddington was a true believer. He had written in 1917 that general relativity was the greatest discovery since Newton. Before any experimental evidence existed, he wanted it to be true. And in the end, he was right. Every subsequent test, from the 1922 eclipse to the 1964 Shapiro time delay to the 2015 detection of gravitational waves, has confirmed Einstein's equations to extraordinary precision. What Eddington proved that day was not just that light bends. He proved that the geometry of spacetime is real. The universe is not a flat stage where forces push and pull. It is a curved, dynamic, living fabric that warps around every star, every planet, every coffee cup you hold. You are sitting in a curved region of spacetime right now, carved by the mass of the Earth beneath your feet. You cannot see the curvature, but your body feels it as weight. That is the ghost of Newton's gravity, the sensation of following a geodesic through a world that is not flat. And that raises the question that still haunts physics today. If spacetime can curve, can it tear? Can it ripple? Can it be woven into something else entirely? The answer, as we now know, is yes. And the story of how we discovered that leads directly to black holes, gravitational waves, and a man named John Archibald Wheeler, who would give these monsters their name. The geometry Einstein described in 1915 was elegant, but it was also terrifying. His field equations were so mathematically dense that only a handful of people on Earth could even read them, let alone solve them. And buried inside those equations was a prediction so strange that Einstein himself refused to believe it for decades. If enough mass is compressed into a small enough volume, space-time does not just curve, it collapses. It forms a boundary called an event horizon, beyond which nothing, not even light, can escape. The first person to take this prediction seriously was not Einstein. It was a young German physicist named Karl Schwarzschild, who was serving on the Eastern Front during World War I. In December 1915, just 1 month after Einstein published his final equations, Schwarzschild wrote a letter from the trenches. He had found an exact solution to the field equations, the first one ever discovered. His solution described the space-time geometry around a single, non-rotating spherical mass. It was beautiful, precise, and it contained a mathematical singularity at a specific radius. Schwarzschild wrote to Einstein, "As you see, the war is kind enough to me, despite the heavy gunfire, to allow me to take walks in your world of ideas." Einstein was impressed, but uneasy. He presented Schwarzschild's solution to the Prussian Academy in January 1916. Schwarzschild never saw the full impact of his work. He contracted pemphigus, a rare autoimmune disease, on the Russian front and died in May 1916 at the age of 42. He was buried in Göttingen, having handed physics a mathematical bomb that would not detonate for another 50 years. The Schwarzschild radius, the point at which gravity becomes inescapable, is not large. For the Earth, it is about 9 millimeters. For the Sun, about 3 kilometers. If you could somehow crush the entire Earth into the size of a marble, it would become a black hole. But in the 1920s and 1930s, this seemed like a mathematical curiosity. No known force could compress a star that much. The idea was dismissed as a quirk of the equations. Then came J. Robert Oppenheimer. In 1939, the same year he published his first paper on nuclear chain reactions, Oppenheimer and his student Hartland Snyder wrote a paper titled On Continued Gravitational Contraction. They showed that a massive star, after exhausting its nuclear fuel, would have no choice. It would collapse inward under its own gravity, passing through the Schwarzschild radius in a finite amount of proper time. From the outside, the star would appear to freeze at the event horizon, redshifting into invisibility. But from the inside, the star would continue collapsing to a point of infinite density, a singularity. Oppenheimer presented this work at a meeting of the American Physical Society in 1939. The response was silence. Most physicists were preoccupied with nuclear fission and the looming war. Oppenheimer himself would soon leave theoretical physics to lead the Manhattan Project. The idea of gravitational collapse was shelved for nearly 2 decades. It was revived in the 1950s by John Archibald Wheeler, a Princeton physicist who had worked on the hydrogen bomb and was now obsessed with the fate of massive stars. Wheeler was the first to realize that Oppenheimer's collapse was not a rare event. It might be the final state of every massive star in the universe. In 1967, at a conference in New York, Wheeler gave the phenomenon a name that stuck: black hole. He later admitted he chose the term because it was short, dramatic, and impossible to misunderstand. But Wheeler did more than name black holes. He asked the question that connects directly back to Einstein's geometry: what happens to space-time inside a black hole? At the singularity, the curvature becomes infinite. The equations break down. Physics, as we know it, ends, and that is where the battle lines were drawn. Einstein had always believed that singularities were a sign that his theory was incomplete, that quantum mechanics would smooth them out. Wheeler was not so sure. He began to suspect that space-time itself might be quantized, woven from discrete threads at the Planck scale, a billionth of a billionth of a billionth of a Horquaz meter. This idea that the smooth fabric of Einstein's geometry might be an illusion, a classical approximation of a deeper quantum reality, would become the central problem of late 20th century physics. It is the problem that Stephen Hawking attacked in 1974 when he showed that black holes are not truly black. They radiate, they evaporate, and that evaporation raises a question so profound It has consumed the careers of Susskind, Tufte, and Maldacena. What happens to the information that falls? Into a black hole? Is it lost forever, violating quantum mechanics? Or is it encoded on the event horizon like a hologram? That debate, the black hole information paradox, is the direct descendant of Schwarzschild's letter from the trenches. It is the unfinished business of Einstein's geometry, and it suggests that the curvature of space-time is not the final word, it is a door. Behind it lies a deeper structure, one we have not yet fully mapped. The geometry that Einstein discovered in 1915 was not the end of the story. It was the beginning of a mystery that still has no resolution. In the 1950s, Wheeler pushed this idea hardest. He had realized that if gravity could crush a star into a singularity, then the classical description of space-time had to break down. The equations scream. Physics stops. Wheeler believed this was not a bug. It was a message. The message was that space-time itself must be quantized, built from indivisible units at the Planck scale, roughly 10 meters, that is 20 orders of magnitude smaller than a proton. Wheeler called this hypothetical structure quantum foam. He imagined that at the Planck scale, space-time is not smooth. It is a churning, frothing sea of virtual black holes and wormholes, popping in and out of existence in Planck time intervals, 10 seconds. The geometry we experience as smooth and continuous is only a statistical average, like the surface of a lake appearing flat from an airplane while hiding the turbulent molecular chaos beneath. This idea was deeply unsettling. Einstein had spent his final decades searching for a unified field theory, a single set of equations that would weave electromagnetism and gravity into a seamless geometric whole. He never found it. Wheeler was suggesting that the very concept of geometry might be emergent, a low-energy approximation of something far stranger. The smooth space-time of general relativity, he argued, was like the surface of a table, solid and continuous to the touch, but a vast empty void of atoms and forces when examined closely. In the 1960s, Wheeler recruited a generation of students to attack this problem. One of them was a young British physicist named Stephen Hawking, who arrived at Cambridge in 1962. Another was Kip Thorne, who went to Caltech. A third was Wheeler-DeWitt, who would formalize the Wheeler-DeWitt equation in 1967, an attempt to write a quantum wave function for the entire universe. The equation was beautiful and almost unusable. It seemed to suggest that time itself disappears at the quantum level. The universe, in this view, is a frozen wave function with no external clock to mark its passage. But the real breakthrough came from an unexpected direction: string theory. In 1968, a young Italian physicist named Gabriele Veneziano was trying to understand the strong nuclear force, the force that binds quarks inside protons and neutrons. He stumbled upon an old mathematical formula from the 18th century, the Euler beta function, which seemed to describe how particles scatter when they collide. Veneziano's formula was elegant but puzzling. It implied that the particles were not point-like. They were tiny, vibrating strings. For years, string theory was considered a mathematical curiosity, a toy model for the strong force. Then in 1974, John Schwarz and Joel Scherk realized something extraordinary. The equations of string theory contained a massless spin 2 particle, the exact signature of the graviton, the hypothetical quantum carrier of gravity. Schwarz and Scherk proposed that string theory was not a theory of nuclear physics. It was a theory of everything. The strings, vibrating at Planck scale frequencies, could generate all particles and all forces, including gravity. This was the first serious candidate for a quantum theory of gravity. It suggested that the fundamental building blocks of reality are not point particles, but one-dimensional strings, each about 10⁻⁹ meters long. The different particles we observe, electrons, quarks, photons, gravitons, are simply different vibrational modes of these strings, like different notes played on a single guitar string. And the geometry of space-time? It emerges from the interactions of these strings, like a melody emerging from the vibrations of a violin. But string theory came with a price. To be mathematically consistent, it required extra dimensions of space, 6 or 7 beyond the familiar 3. These dimensions, the theory argued, are curled up so tightly at the Planck scale that we cannot see them, like a garden hose that looks like a line from a distance, but reveals a circular cross-section when examined closely. This idea, called compactification, was first proposed in the 1920s by Theodor Kaluza and Oskar Klein, who tried to unify electromagnetism and gravity by adding a 5th dimension. String theory revived their idea and multiplied it. By the 1980s, string theory had become the dominant research program in theoretical physics. Edward Witten, a prodigy from Princeton, emerged as its intellectual leader. In 1984, Witten, Schwarz, and Michael Green published a landmark paper showing that string theory was free of the mathematical anomalies that had plagued previous attempts at quantum gravity. The theory was consistent, it was beautiful, and it was untestable. The energy scales required to directly observe strings, the Planck energy of 10 MeV, are trillions of times beyond the reach of any particle accelerator ever built. This created a deep tension. Einstein's geometry had been tested and confirmed, from the 1919 eclipse to the 2015 detection of gravitational waves. String theory, by contrast, remained a mathematical castle in the sky with no experimental foundation. Critics, including Nobel laureate Sheldon Glashow, called it a theology rather than a science. Proponents, led by Witten, argued that the mathematical consistency of the theory was itself a form of evidence, that nature would not be so elegant for no reason. In 1995, Witten made a move that changed everything. At a conference at the University of Southern California, he proposed that the 5 different versions of string theory were not separate theories at all. They were different limits of a single, deeper theory, which he called M-theory. This theory lived in 11 dimensions, 10 of space and 1 of time, and it contained not just strings but 2-dimensional membranes, or branes, and higher-dimensional objects. The geometry of space-time in M-theory was not fundamental. It was a shadow cast by the interactions of branes in higher-dimensional space. This idea led to a stunning conjecture, the holographic principle, first proposed by Gerardus de Hooft in 1993 and refined by Leonard Susskind in 1994. It suggested that the entire 3-dimensional volume of our universe might be encoded on a 2-dimensional surface at its boundary, like a hologram. The geometry we experience as depth and distance might be a projection, a higher dimensional illusion. The information content of a region of space is not proportional to its volume, but to its surface area. This was a direct challenge to the smooth, continuous spacetime that Einstein had described. The holographic principle was not merely a clever mathematical trick. It was a fundamental rewriting of how many dimensions reality actually contains. For decades, physicists had assumed that the information stored inside a black hole was proportional to its volume. The bigger the hole, the more data it could swallow. But in 1972, Jacob Bekenstein, a graduate student at Princeton, had noticed something strange. He calculated that the entropy of a black hole, a measure of its hidden information, was proportional not to its volume, but to the area of its event horizon. It was as if the black hole's entire interior was encoded on its 2-dimensional surface, like a 3-dimensional object projected onto a flat screen. Stephen Hawking initially fought this idea. He argued that black holes could not have entropy because they were perfect absorbers. They erased all information that fell in. But in 1974, Hawking himself proved that black holes radiate. They emit thermal particles from just outside the event horizon, slowly evaporating over cosmic time, and that radiation carries no information about what fell in. This created a paradox. If a black hole evaporates completely, all the information about its past is lost forever. Quantum mechanics, the most successful theory in physics, absolutely forbids information loss. The universe cannot forget. Leonard Susskind, a physicist at Stanford, saw this as a declaration of war. In 1981, at a conference in San Francisco, Susskind confronted Hawking directly. He argued that information cannot be destroyed. It must escape the black hole somehow, encoded in the Hawking radiation itself. Hawking was unconvinced. The debate raged for nearly 3 decades. In 1997, Hawking made a public bet with John Preskill, another Caltech physicist, wagering that information was indeed lost. Susskind and 't Hooft took the opposite side. The stakes were not money, but the fundamental structure of reality. The resolution came from an unexpected direction: string theory. In 1997, Juan Maldacena, a young Argentine physicist at Harvard, published a paper that would change everything. He proposed a duality between a universe with gravity in 5 dimensions and a quantum field theory without gravity on its 4-dimensional boundary. The two descriptions were mathematically equivalent. The curved, gravitational interior of the universe was a hologram projected from its flat, gravity-free surface. Maldacena called it the APHI-SSCF correspondence, and it was the most concrete realization of the holographic principle ever discovered. What Maldacena showed was that a black hole in the 5-dimensional bulk of anti de Sitter space corresponds exactly to a hot, thermalized plasma on the 4-dimensional boundary. The information that falls into the black hole is not lost. It is encoded in the quantum state of the boundary particles. The black hole's interior geometry is a mirage, a collective description of the entangled degrees of freedom on the surface. This was not speculation. It was a precise, testable mathematical duality, backed by hundreds of papers and thousands of calculations. Hawking conceded defeat in 2004. At a conference in Dublin, he announced that he had been wrong. Information does escape black holes, carried out by subtle quantum correlations in the Hawking radiation. He paid off his bet with Preskill, handing over a baseball encyclopedia from which he could extract information at will. The room erupted in applause. But the deeper question remained: if our universe is itself a hologram, what does that mean for the geometry we experience every day? And that is where the mystery stands today. Einstein's curved spacetime is not wrong. It is confirmed by every experiment we have ever performed, but it may be incomplete. It may be the classical limit of a deeper quantum reality, one that we have not yet fully grasped. The geometry that Schwarzschild solved in the trenches, that Eddington verified under an African eclipse, that Wheeler called quantum foam, and that Witten wove into M-theory, it is still a work in progress. The final shape of reality has not been drawn.